Yes. So with those few examples, let's move on to the next topic, which is properties of Fourier transform. Okay, so there are 13 properties. We will see one by one. So first one is linearity property. So we have seen this even for Fourier series. So most of the properties will repeat here. The notation will change. Okay. So first property is linearity. So what does it say? If, okay, so let us take x1 of t has x1 of j omega as the Fourier transform, and another signal x2 of t has x2 of j omega as the Fourier transform, then the linear combination of these two signals, which is a times x1 of t plus b times x2 of t, will have what as Fourier transform? Will have a times x1 of j omega plus b times x2 of j omega as the Fourier transform. What does it say? If you take linear combination in time domain, you should take the same linear combination in the frequency domain. So let us try to prove this result. Okay, it is simple, but let us try to prove it. Okay, so let's assume this ax1 of t plus bx2 of t as x3 of t. Okay, so let x3 of t equal to ax1 of t, okay, plus bx2 of t. So let us take this fellow's Fourier transform. So let us call that to be x3 of j omega. So x3 of j omega would be equal to how much? Integral minus infinity to infinity x3 of t multiplied with e power minus j omega t dt. So this is equal to how much? Integral minus infinity to infinity ax1 of t plus b times x2 of t, correct? By x3 of t we assume it to be ax1 of t plus bx2 of t, and this fellow is multiplied with e power minus j omega t and then multiplied with dt. So clearly, because integral operation is linear and a and b are constants, this can be written as a times integral minus infinity to infinity x1 of t, and we can assign e power minus j omega t to each fellow, e power minus j omega t dt plus b times integral minus infinity to infinity x2 of t e power minus j omega t dt. So clearly, what is the first integral here? First integral would be x1 of j omega, and what about the second integral? You will get b times x2 of j omega. So what does it mean? That if you take linear combination of the signals, the corresponding Fourier transform also would be linear combination. Okay, so in that way, and that we call it as what? Linearity property. So now let us take a few examples. Okay, so example, so we are interested in finding, okay, so we'll write down find CTFT of the following signal. Okay, so find the CTFT of the following signal. Okay, so what is that signal? It is a staircase signal. Okay, so let us take this fellow from -3, -2, 2 to 3, and amplitudes are 1 and 2. Okay, so let us call this signal as x of t. So we want to find the Fourier transform of this signal x of t. So you can easily see that this signal satisfies what properties here? The signal will satisfy all the three Dirichlet conditions, and hence you can use our regular analysis equation. So what do I mean by that? So you can see that our x of j omega is how much? Integral -3 to -2, amplitude is 1 e power minus j omega t dt, plus integral -2 to +2, amplitude is 2 e power minus j omega t dt, plus finally 2 to 3, amplitude is 1 multiplied with e power minus j omega t dt. So you can do this integration and then simplify, but that is little bit laborious, so I will put a question mark there. So if you are interested, you can do this integration. But if you are smart, you can easily see that staircase signal can be written as, okay, so I'll write down little bit, correct. That staircase signal can be written as summation of two signals. Okay, so one is a rectangle from -3 to +3 with amplitude 1. Let us call this signal to be x1 of t, plus so another rectangle signal from where to where, from -2 to +2 with amplitude 1, and let us call this signal to be x2 of t. So what is that you see here? You see that x of t can be written as this signal x1 of t plus x2 of t. So let us write down that. So but before we write down, we already know the Fourier transform of these signals. Okay, so what is that? X1 of t will have what as Fourier transform? 2 sine omega t. Capital T is 3, so you get 2 sine 3 omega by omega. Similarly, what about x2 of t? What is this fellow's Fourier transform? That fellow's Fourier transform is 2 sine omega t. T is again 2 for us, so we'll get 2 sine 2 omega by omega as the Fourier transform. Now, just now we have seen that our original signal x of t can be written as x1 of t plus x2 of t. So we want Fourier transform of this signal. So by using linearity property, what do you get? You get the Fourier transform to be x1 of j omega plus x2 of j omega. Why? The scaling factors are what? 1 and 1, and hence here also you'll get scaling factors to be 1 and 1. But what is x1 of j omega? This is our x1 of j omega. Why? x1 of t will have x1 of j omega, and this fellow would be our x2 of j omega. So what would be the final answer? This is our x of j omega, right? So x of t will have x of j omega, which is nothing but x1 of j omega plus x2 of j omega. So what would be the answer? You will get 2 sine 3 omega whole divided by omega, plus this would be 2 sine 2 omega whole divided by omega. Okay, so finally what is the answer here? This denominator is omega, so which is common, so you will get 2 times sine 3 omega plus 2 omega whole divided by omega. So you can, sorry, I missed sine here. Okay, so sine 3 omega plus sine 2 omega whole divided by omega. Okay, you can further simplify. Why? The numerator term is looking like sine A plus sine B. You can further simplify that. I will leave it for you. Okay, so what is that we got? We got the answer that the following staircase signal, okay, which is given by this plot, will have what as Fourier transform? This is -3, -2, 2 and 3 with amplitudes 1 and 2. This is our x of t. This fellow will have 2 times sine of 3 omega plus sine 2 omega by omega as the Fourier transform. So if you, this is one example, but if you remember, we have already used the linearity property where to find Fourier transform of e power minus a mod t, correct? So we got this to be how much? E power minus a t u of t plus e power a t u of minus t, correct? So here we again used linearity property. One more we have used where to find Fourier transform of u of t. So what is that? We got u of t to be how much? 1 by 2 times 1 plus signum of t, correct? So this here also which property we have to use? We have to use linearity property. We have used it actually to find the Fourier transform of u of t. So what is that? This is nothing but 1 by 2 times Fourier transform of 1 plus Fourier transform of signum of t. So in that kind of splitting the Fourier transform, we call it as what? we call it as linearity property. Okay, so in that way we can, it's very helpful. So if the Fourier transform doesn't satisfy linearity property, we are in trouble. Okay, so let us be thankful that Fourier transform satisfies linearity property. Okay.